Hey everyone. So last time we ended our discussion on energy and the flow of energy, and how energy was kind of the fundamental building block of the universe. And so we're going to take a step up the fine graining now. We're going to go from energy to now talking about atoms. And atoms are fundamental building blocks of everyday matter that we interact with. So this is under the umbrella of modern atomic theory. Before we start talking about elements, we're going to talk about what it is, or what they are, and what their symbols are. And so, in a chemical sense, what this means is that elements are kind of our finest building block we're worried about in chemistry, and so they cannot be broken down into smaller substances. And we know, as physics has advanced, that this isn't necessarily true. Things like uranium and other atoms can be broken down into other subatomic particles, and we would touch on those a little bit. For chemical for chemical reasons, we deal with elements as the fundamental building block for chemistry. And so, how do we define elements? Elements are usually defined by a 1 or 2 letter symbol. Only the first letter of an element is capitalized. If the symbol has a second letter, that's usually written as a lowercase letter, and it's not capitalized. And so, for example, we have 2 different symbols here, and they actually mean 2 different things in chemistry. C, capital C, and lowercase o. This represents the element cobalt, right? Where uppercase C and uppercase O, this represents the molecule carbon monoxide, which you guys may have heard is a toxic chemical for if we breathe it in. So it's important to distinguish elements from molecules by upper and lowercase letters. Elements are separated within molecules by upper and lowercase letters. So cobalt is a relatively intuitive one, but a lot of the elements get their name from their Greek or Latin names. So for example, Na comes from natrium, but this element is called sodium. The same thing like in sodium chloride, like what you have in your table salt. Fe is a Latin name, ferrum, but this is what we refer to as iron, a metal that a lot of us are very familiar with. And so this is how we give symbolism to our elements and how we actually deal with them, right, is through these letters. Again, first letter is capitalized. If there is a second letter, it's lowercase. There doesn't always have to be a second letter. And so this is for all what we would call monoatomic elements. Some elements, however, in their natural forms, they don't exist as atoms. These exist as what we call diatomics, right? Where the prefix di, and we'll talk a lot about prefixes in the next coming days. The number of atoms, and di means 2. These exist as diatomics in their natural state. So for example, when you refer to hydrogen, you refer to H2. When you refer to oxygen, we refer to O2, at least in an elemental sense. Nitrogen, we refer to as N2. Fluorine, we refer to as F2. Then we have chlorine, bromine, and iodine. Right? And so what this means is that when you have two hydrogen atoms, they bond together like this in their natural state. They don't just exist as a floating hydrogen atom, whereas something like sodium can exist as a sodium metal on its own in that own state of matter. And where do we see these elements and symbols? Well, we see these on what we call the periodic table. And so elements are organized in a logical way on the periodic table, and we'll talk about how these elements are organized here. And there's a couple different ways that they are organized. In this blue block, these are called our metals. What is defining a metal? Well, we'll go into more detail later, but metals are basically going to be things that are easily donating electrons. In this small green section here, we have what we call the metalloids, and then in the yellow we have non-metals. So this is one way that we can look at the periodic table. Really, the periodic table is actually organized in a much more rigorous way about certain properties of each of the elements, but we can look at a lot of different things at the periodic table this way. Look at it this way, there's some things that we can define for these elements, right? Metals are going to be mostly solid, have shiny appearances, which we're used to. They're good conductors of electricity and heat, which is why we use them in electronics. They're malleable and ductile, meaning that they can bend easily and be melted, reformed into vastly different shapes. And they tend to lose electrons, right? So this is, an interesting property of them because this actually describes their chemical behavior quite a bit. Then we have nonmetals. These are usually solid, liquid, or gas. They have dull appearances, meaning that if you were to have a powder of them, they wouldn't be shiny at all. They're usually poor conductors of heat and electricity, brittle, and then they gain or share electrons. This is, again, commenting on their chemical behavior generally, right? So there's some properties of both of these. And then metalloids are going to have both properties of metals and nonmetals, right? And so these are interesting elements, and two of the most important ones are going to be silicon and germanium. And the reason that they're interesting is because they have properties of nonmetals, right, where they can be somewhat insulating in terms of electrical conductivity, but then they can sometimes be conductive. So these are used a lot in the synthesis of things like computer chips, solar cells, thermoelectrics, and just electrical devices in general. And they have very interesting properties because of this kind of region that they exist in between non-metal and metal behavior. So these metalloids have both properties of metals and non-metals, right? So if we go back here, they may have a dull appearance, but are still a good conductor of heat electricity, like the case of germanium. Or they can be mostly solid, like silicon, right? But brittle, like silicon, for example. It can be brittle, like a thing of solid bromine or iodine crystals. And so the periodic table is organized by the structure of the different rows and columns, and these are related to the atomic structure. Like, how do we define what these atoms are that belong in these rows and columns? The periodic tables I've shown here only have the metalloids filled in, but really each individual spot here is all going to have a different atom, meaning a different elemental symbol there. And so the columns, these are called the groups on the periodic table, right? So these are the groups. And then the rows, right? So these are the rows. These are called the periods on the periodic table, right? So that's where the name comes from, periodic. And so that's how we define the two rows and columns. And so the groups are organized by the valence. And what valence means? The outermost electrons. And the periods are organized by the energy levels within the electrons. And we'll talk about what that means a little bit later. But that's how we are organizing these chemically. And each of these groups and periods, they have different names, right? So the important ones for us in biology are usually called the main group elements here, This is from 13 to 6. Group 7, right? So that it says 13, 14, 15, 16 here, but the group number is actually related to this, and that's because this whole center region actually behaves a little bit funky. We call this region the transition metal region. That's because their valence electrons behave a little funky. So that's why we kind of skip over group numbers for them. These are still technically considered different groups here, but we number these in the way where we go 1A, 2, 3, 4, 5, 6, 7, 8. We kind of skip over the numbering when we talk about the transition metal region. So the transition metals, again, those have interesting behavior. Then we have the halogens in group 7. In group 8, these are called the noble gases. Group 2 are called the alkali earth metals. And then group 1, they're called the earth metals. All right, so we see if we were looking at things before in terms of metal, non-metal, they kind of still follow this trend a little bit, but these are the specific names of the groups here, right? So again, the groups are the columns. We have our main group elements, which are relevant for biology. Not that the other ones aren't, but this is probably the most relevant. They're halogens, noble gases, transition metals, which is this long big block here, alkali earth metals, and then our alkali metals. And so before we get into what are these individual elements that we've been talking about, we kind of have to discuss, what is the structure of atoms? And so there's a little bit of a history to that, right? And so the first early theory of atomic structure, meaning what makes up atoms, is that each element is composed of tiny indestructible particles called atoms. And all elements of a given atom are similar to one another, but different from another. So meaning that if we had an elemental substance like fire, then fire would be similar to other fire atoms, but different from, say, water atoms in a very simplistic way. And then these atoms would combine in simple whole number ratios to form compounds. So as to say, we had these little atoms, right? Oxygen atoms, small individual particles. These would then combine to form oxygen compounds, right? And so that's what the early theories of atom was, just this kind of what we'd say discrete nature of matter, right? We don't have a continuous, wood isn't necessarily a continuous object, but it's composed of compounds and atoms that are indestructible and indivisible parts of that matter itself. And so the first kind of break in these early ideas of what atomic structure was came from the discovery of one subatomic particle called the electron, right? And so electron is a small negatively charged particle. And so smaller than atom particles exist. These are called subatomic, right? Meaning they're smaller than the atom itself. And in 1897, J.J. Thomson performed an experiment with a cathode ray tube. And so what happened is they basically had all these excited atoms here, right? They had all these excited atoms here that then were pumped into a vacuum, and the atoms were then excited with some form of energy, and they let out a beam of something like this. And they put this in an electric field, so you have a positive side and negative side, which means we go from positive to negative, like this electric field. And what happened is it caused a curve in the beam, which means that there was something in these atoms that are ordinarily neutral that was being deflected by the beam. And the way that the beam curved towards the positive side, right? This meant that these were negatively charged particles, right? And so his experiment showed, okay, there's something in atoms that we know are going to be negatively charged. So once this discovery was made, the earlier, Dalton's atomic theory was revisited and changed a bit, right? Because this is how science works. We don't ever hold any theory as absolute fact. In fact, a theory only stands as long as it hasn't been disproven yet, right? So once the theory's been disproven, it's okay, we got to go back and modify things and look at things a little bit more closely. And so based off of his findings, Thomson proposed an atomic model where you basically have a composed uniform sphere of positive charge that then has little electrons inside of it. And so this is called the plum pudding model, right? So it's like we have a uniform sphere that represents the pudding, and then there's little plum electrons in there that then can move around within within this charge, or this uniformly positively charged sphere. And the reason that we need the positive charge is because even though we found these subatomic negatively charged electrons, we still know that most matter is neutral, meaning that it doesn't have any net charge. So most matter is going to be neutral. But there are these negatively charged particles in there. So that means that most of the time we have to have something that counteracts that negative charge. And that's what the uniform positive charge was developed for. And so then further experiments were done. So they were done by a guy named Ernest Rutherford. And he carried out a series of experiments where basically we had a little piece of gold and you bombarded it with a source of radiation. So these are called alpha particles, denoted by that Greek symbol here. Alpha particle is really composed of two other subatomic particles, a proton, two protons and two neutrons. And these are very interactive, meaning they strongly interact with certain other massive particles. And in these experiments, he bombarded thin sheets of gold with these alpha particles. Right, so these alpha particles, I didn't mention, also have a charge on them, a +2 charge. And what he observed is that most of the time, right, alpha particles go straight through the gold foil. And you said, okay, this is weird. I thought that, matter was composed of these uniformly positive spheres that had little electrons floating around. These positively charged particles that I'm bombarding this gold foil going through at this moment. And so what he devised was that, okay, really what's happening in these in this gold foil is that we have these atoms that are all bonded to each other. And most of the time, my alpha particles, they're just going straight through, which all these black lines, right? All the black lines is the majority of time, these alpha particles are going straight through. However, every now and then, they reach, or they perfectly line up with something that then causes the alpha particle to either be deflected or scatter, right? So what scattering is just the deflection of the particle. And so now you get a little, on your sensor, right, you get a little reading somewhere else that's not right behind the gold foil. So your sensor says, hey, we have, a alpha particle hit over here. And the theory that he came up with is that actually what matter is made up is mostly empty space, because most of the time alpha particles go straight through. Or, things that it doesn't interact strongly with, like the electrons, it doesn't interact with them most of the time. However, a small percentage of the time it interacts with something very dense and positively charged, because the alpha particles are bouncing away from them and like charges repel from each other, right? So this is actually, the nucleus has to be something, there has to be a small, tiny nucleus inside these atoms that contains all the positive charge, and then most of the atom is kind of taken up by this empty space. And so the modern atom, how we think of it, is that the nucleus is consisted of positively charged, what we call protons, right? So P with a positive charge, and neutrally charged neutrons, right? So the nucleus takes up 1/10,000 or 1/1000th of the entire volume of the atom, but it has all the positive charge and also this extra mass from another subatomic particle called neutrons. The electrons, which we talked about earlier, move rapidly throughout the atomic volume, and they're held together by attractive forces, and these attractive forces are what we call Coulombic forces, which is just positive and negative charges attracting each other. So the atom itself is actually mostly empty. The space is taken up by, rapidly moving electrons, and then the nucleus contains almost all of the mass of the atom, right? So the nucleus contains all mass of the atom and takes a very, very small volume, right? So very small volume for the atom, which is why the particles went through. And so these subatomic particles, right, we see that protons, they're going to be positively charged because you still need positive charge to counteract the electron to maintain neutrality of matter. Otherwise, matter would just annihilate. And the relative mass of protons and neutrons is much, it's about 2,000 times larger than that of electrons. So almost all the mass is contained in the nucleus. And so this gives us the structure of the atom, right? So we haven't talked about the energies of any of these subatomic particles yet, but this gives us the entire structure, or at least what it's composed of. So it wasn't until these experiments that, we devised a theory, right? We said, okay, well, we know that there has to be something positive charge because electrons do exist. And then based off of this counteracting of the positive charge, that doesn't account for all the mass, so there has to be another particle there that's accounting for some of the mass, which is where we got the neutron from. Okay, so this gives us the atomic structure, and then this gives us the general designation for what an atom looks like, right? And how we can define an atom. So this is called isotope notation, right? Where X is the chemical symbol, right? This is what's on the periodic table. We have in the upper left-hand corner, this is the mass number, A, which is equal to the number of protons plus the number of neutrons. And then we have the atomic number Z, which is the number of protons. And what we're going to be learning here is that the number of protons and the number of neutrons, right? This gives us the total mass of the element. The number of protons, this gives us the identity of the element, and the structure of the electrons is what's going to give us the personality, the reactivity of the element, right? And so this is how we write an element in isotope notation. We're going to talk about what that means in a second. And so elements can have the same atomic number, Z, right? So Z equals number of protons, remember? And this is the number on the periodic table that you see, right? So if we were to look at the periodic table, you would have something that has the elemental symbol here. It'll have the mass number here, and then in the upper right hand or left hand corner, you have the atomic number Z. So the identity is given by the atomic number, but for isotopes you can have different masses. So you have the same number of protons but different number of neutrons, right? So here we have an example of hydrogen and 3 different isotopes of hydrogen. So hydrogen is the simplest element, has 1 proton and 1 electron in this isotope called protium. Deuterium, right, this is the most abundant form. Deuterium is going to have 1 proton, one neutron and one electron, it still has the identity of hydrogen because it has one proton. And then tritium is going to have two neutrons and one electron, right? So it still has the identity of hydrogen because it has one proton, but now it has two extra neutrons. And so that's why, or that's how we define what isotopes are, right? It's the same atomic number, but different masses. And that's because in nature, based off the different forces that hold things together, it isn't just electrostatic forces, it's actually other things like the strong and weak force. And these things are what actually hold the nucleus together. And so the mass of an atom is measured relative to the mass of some chosen standard. So carbon-12 atom. And it's expressed in units of atomic mass units, or AMU. And the average atomic mass is what you actually see on the periodic table, right? So earlier, when I said this was the mass number right here, this is the average atomic mass. And the average atomic mass comes from all the different possible isotopes that you have of that element, meaning the same number of protons and different number of neutrons, and it's weighted according to their abundance. What does that mean? That means what is the most prevalent version in the universe. And so atomic mass of an element is closest to that of its most abundant version. And so let's see, what does that actually mean? Okay, so if you have something like, let's say hydrogen, and we had the three different isotopes, protium, tritium, and deuterium. If this was 95% abundant and this was 1 AMU, this was 3 AMU, and this was 2 AMU, this was 1% abundant, and this was 4% of the universe of all hydrogen, that means that the atomic mass, the average atomic mass, can be close to this one because there's more of it present in the universe, which is why we see it on the periodic table under the average atomic mass. And so how would we use these? And use isotope notation in terms of determining things of an element. So if you're given an element with a specific isotope notation, you could be asked, okay, what are the number of protons, electrons, and neutrons within this chlorine atom? Well, how do I know it's chlorine? Well, there's two things that tell me it's chlorine, right? The number of protons, and if you look it up on the periodic table, the atomic number 17 corresponds to the elemental symbol Cl, right? This is what tells us that it's going to be chlorine. And that tells us right away that the number of protons equals 17. We see that this is a neutral element. If there was a charge here, the charge would be located right here, but since there's nothing, that means the charge is 0. And for neutral matter, the number of protons matter implies that number of protons equals the number of electrons, which means that the number of electrons for this element is 17 because we have 17 protons. And then the mass number, this is A, is equal to the number of protons plus the number of neutrons. And so if we wanted to determine the number of neutrons in this isotope, or this whatever isotope of chlorine it is that we have here, we would have 35 is equal to 17, because that's the number of protons, plus the number of neutrons. And I'll just put the number n there. So that means that if we subtract 17 from both sides, minus 17, then we would get 18 is equal to the number of neutrons, right? So that's how we would use isotope notation to determine all this relevant information about this isotope. We get the number of protons, number of electrons, and the number of neutrons just from this small little symbol here. And so if we were to calculate the average mass from the isotopic data, and that means that we had something like the abundance available to us and the relative mass of the isotope, the relative, this was abundance, And we can think of abundance equals the percentage that exists in the universe. And so this abundance, like how would we get the average mass for these elements? Like what would we actually see on the periodic table? We can calculate the average of something if, let's say, we want to find the average of some variable x. We can have the percentage of one variable times the value of that variable plus whatever the other percentages are of the other variables that represent the quantity that we're talking about. So this will be x1 value and this is x2 value. You say, okay, well, what does that mean? How do we actually use that? Well, let's use it for the average mass. If I want to find the average mass for Ag, which is silver, how we'd use that based off this table is I'd say, well, the mass of Ag107, mass of Ag107 times its abundance percentage, which is 0.5184. Right? Whenever we use a percentage, we have to divide by 100, which is why it becomes 0.05184, plus the mass of Ag109 times its abundance, which is 0.4816. Right? So you plug in the numbers where this mass is that one right here. This mass is that one right there. And that's how you get the average mass, and that's how they use the average mass on isotopic data. I'm not going to go through and finish this calculation because it's actually an example for you on the work through example on the Canvas page. But this is how you would use this. And if you had 3 different isotopes, for example, then all you would need is one extra term for the third isotope. All right, so that's how we calculate the average mass. And so once we've discovered and talked about the structure of the atom and a little bit of the structure of the nucleus, then we can get to even more modern atomic theories. And so Bohr, Niels Bohr, was a famous physicist during the same time as Einstein, and one of the fathers of what we call quantum mechanics, came up with a new model of the atom that embodies the importance of electron arrangement around the nucleus itself. And so Bohr's model of an atom basically said, well, we actually have electrons orbiting around the nucleus, right? So these are all possible electrons that can orbit around the nucleus, kind of like our planet orbits around our sun. And these could only exist at very distinct orbits, meaning very specific distances, right? So each of these distances was one possible orbit for an electron. And what that means is that these orbits, keep writing this wrong, these orbits were quantized. Right? And this is where the name quantum mechanics kind of comes from. But these orbits are quantized. And what that means is that they're very discrete. They're not very discrete, but they're discrete orbits. Meaning there's only specific orbits that these electrons can actually exist at. And this was important for the model of the atom, because electrons, they had to be moving in some sort of fashion around the nucleus based off of Rutherford's experiments. And then they were finding out very interesting things about matter. For example, certain spectral data from the sun show that there's gaps with certain energy values that they read from the sun. And that had to do with this quantization of these orbits that electrons could exist at. And so why was that important for the structure of atoms? Well, it had to do with the way that energy behaves, or how electrons are able to move through these different orbits. And the lowest energy that an electron can exist at, the energy level is related to the orbit, and that's called the ground state. And any higher energy levels are called excited states. And so when electrons absorb energy through either heating, electricity, or most commonly through light, right, they can move through these orbits, right? And so the Bohr model gave a way for electrons to only exist. Electrons can only exist at specific energy levels. And so because they could only exist at specific energy levels, when these electrons move between them, the only way they could do that is through releasing or absorbing energy in the form of light. However, Bohr's model was still not completely complete because it didn't explain the electron behavior of large atoms, and also because if an electron is actually spinning, right, eventually it should spiral down and decay because it releases radiation as the electron is moving in a circular motion. And if this was happening, then eventually all electrons would fall into the nucleus and then matter would annihilate, right? So that still doesn't solve the problem of decaying orbits, but it did bring up this new idea of quantization of energy within atoms. And so this quantization we could then measure and observe through the energy of light that we look at. And so the excitations mostly come from the release or absorbance of electromagnetic radiation, which is just a form of light. And it had been determined already by a guy named Maxwell that the energy of light is E equals h nu, right? So this is the energy in joules. H is a fundamental constant of the universe called Planck's constant, and it has a value of 6.626 times 10 to the minus 34. And the units are joule seconds. Nu is the frequency of light, and the frequency is related to the speed of light. Speed of light, which is 2.998 times 10 to the 8 meters per second. And C is related to the frequency, as lambda nu. All right, so if this is in units of meters per second, nu is going to be units of inverse seconds. Lambda is defined as the wavelength and has units of meters. And so all these things come together to give us the energy of light. And because we have now these quantized orbits of light, we could then observe the structure of atoms by looking at how matter interacts with light. And so we can calculate the energy of light emitted or absorbed within atoms from Bohr's simple model by looking at the excitation or the energy of excited electrons moving from one level to another. And from the simplified model, the relationship that we get is called the Rydberg equation. And the Rydberg equation says that 1 over the wavelength of light that's emitted is equal to the Rydberg constant, R sub h, times 1 over n f squared minus 1 over n I squared. And what are these n's? These n's are the principal energy level of the lights or the electrons before and after excitation. The Rydberg constant is a fundamental constant related to other things in the atomic structure, and its value is 1.097 times 10 to the minus 2 inverse nanometers. Right, and so we have 1 over the wavelength, so we should have inverse units of length here. And so each of these NF, this was the final energy level, and this is the initial energy level. And so this simplified model, Bohr model, which isn't exactly how atoms actually behave, allowed us to then calculate the wavelength of light that we should be seeing. And this is what led to something called the ultraviolet catastrophe, and ultimately revisiting of the Bohr model of the atom into what we call modern atomic theory. And so how would we use this? Well, if we were to calculate the energy of a photon that's emitted from relaxation of an n equals 2 to an n equal 1 state, we would use the Rydberg equation to first calculate the wavelength, right? First step would be calculate lambda. And then the second step would be to calculate the energy using E equals h nu and the relationships between all of those. So in step 1, we have 1 over lambda equals the Rydberg constant times 1 over n final squared minus 1 over n initial squared. So we have to be careful when we're doing this calculation, because we need to make sure that we're doing 1 over these quantities squared subtracted from each other, and not 1 over these quantities subtracted from each other squared. So we have 1.0, the value was 97 times 10 to the minus 2 inverse nanometers. And then we have our relaxation, meaning we started in the n equals 2. So this is going to be our n initial to our final, where we end up in the n equals 1 state. So we end up in n equals 1 squared. So 1 over 1 squared, which is just 1 divided by 1 over 2 squared. All right, the n value is just the actual number. This is called a quantum number. Lambda is equal to 1.097 times 10 to the minus 2 inverse nanometers times 1 over 4. So 1 over the wavelength is going to be, we plug this in our calculator, 1.097 10 to the minus 2 inverse nanometers, 3 over 4, and we get, sorry, I don't know why that just got minimized. Looks like this should have come to lectures, modern atomic theory. Okay, so the Rydberg constant times this gives us value for 1 over lambda equals 8.230.298 times 10 to the minus 2 nanometers inverse, which gives us 1 over lambda. If we convert this to meters, and the reason we have to convert this to meters is for the equation of light. We have to make sure all our units work out. 8.23 times 10 to the 6 inverse meters, which means that if we want to solve for lambda, we multiply it by lambda to both sides. right? That cancels out on the right side. And then we divide by this number times 10 to the 6 inverse meters. 23 times 10 to the 6 inverse meters. And so now lambda is equal to 1 over this number, inverse meters. And so now we can plug this into our calculator, and that'll give us the wavelength. And so this gives us a value of 1.22 times 10 to the minus 7 meters, right? Because when we divide by inverse meters, the units of 1 over meter, same thing as writing 1 over meter, which just gives us meters in the numerator. So that's how we end up with just units of meters in the numerator. So this gives us the wavelength. This is the first step of the problem, because now we need to use this wavelength to solve for the energy of the photon, right? So we use E equals h nu, which is the same thing as E equals c, or nu times lambda, is equal to the speed of light, because it's a fundamental constant in our universe, which means that nu is equal to c over lambda. We can substitute this into our equation here to give us E equals hc over lambda. So you get E equals hc, or h nu, or sorry, hc over lambda, which is 6.626 times 10 minus 34 joule seconds, times the speed of light, 2.998 times 10 to the 8 meters per second, which is why we had to change lambda into units of meters, over 1.22 times 10 to the minus 7 meters. So now units of meters cancels out, seconds cancels out with seconds there, and all we're left with is joules, which is our unit of energy, which is what we want. So we plug this in, and we get the value of 1.63 times 10 to the minus 18 joules. So that's how we calculate the energy released by an excited electron within an atom. So we're going to take a break for this lecture here. Next time we're going to start talking about the specific electron structures within atoms. And that's going to be related to the quantum mechanical model of the atom, right? So we're just barely scratching the surface of what quantum mechanics is.